Okay, what's up? Math and Beats videos, and we're gonna look at an example on using the contrapositive to prove a statement. Let's look at it. Okay, so first thing here, this example, we're going to use the contrapositive to prove specifically an implication. So contrapositive to prove an implication. Okay, now before we look at what we're going to try and prove, let's just recall what the contrapositive of a logical implication is, just to remind you. So say we got two statements, P and Q, then we get the logical implication, P implies Q. The contrapositive of that is the statement, if not Q, then not P. And more importantly, these two statements, the contrapositives of each other, they have the same truth tables. So hence they are logically equivalent statements. That means if we were able to prove one of the statements, we automatically prove the other one as well. So we're going to use that to show how we can prove an implication. And here is the statement that we're going to try and prove. That is, if a product of two positive numbers is greater than 100, then at least one of the numbers has to be bigger than 10. So it seems reasonable, right? You got two positive numbers being multiplied to give you some number bigger than 100. Then how would you be able to multiply two numbers to get that result where one of them is at least not bigger than 10? So we want to prove this. Maybe we'll just call these two positive numbers whatever they are. Let's call these two things X and Y, just to keep track of them. Okay, so we're going to first write the statement using quantifiers, and then the goal is to use the contrapositive of this statement to prove the actual statement. So here, that I just underlined, there is the statement we just discussed above, written using quantifiers. So remember, we called our two positive numbers X and Y. So what we're saying is, okay, look, for any positive numbers X and Y, think of this as if the product of them, X times Y, is bigger than 100, then either X is bigger than 10, remember the symbol, or Y is bigger than 10, or maybe both, but at least one of them. So that's the statement written using quantifiers. And now we're going to rewrite that statement as its contrapositive. So what is the contrapositive of the statement? That is, okay, still assuming we got two positive numbers X and Y, then we negate the conclusion of the statement, and that is we negate this part up here. Think of that as like your Q. So this is not Q. And then this statement right there, that first one, is P. And as you can see down below here, this is not P. So what does it say? Not X is bigger than 10 or Y is bigger than 10. If that, then not X times Y bigger than 100. So it's kind of strange to say it that way. So we'll rewrite it so it makes a little more sense. What's that equivalent to? For every positive values, positive numbers X and Y, you have for every X and Y that is less than or equal to 10. So that's negating the not X bigger than 10 or Y bigger than 10. So think about what the negation of that is. First statement is saying one of these values, X or Y, is bigger than 10. So the negation of that is both of them are less than or equal to 10. So again, this is not Q over here, implying that, well, again, the negation of P over here, that's like saying in the inside, in the parentheses, you have a product that's bigger than 10 of two numbers. The negation of that is, well, the product is not bigger than 100. Excuse me, I said 10 a moment ago. Bigger than 100. That means the product has to be less than or equal to 100. So we get not P over here. So we're going to prove that statement. And again, the whole point is we're going to prove the contrapositive, and then that will show the original statement, if P then Q, also true, since the contrapositives of each other are logically equivalent. All right, so the proof isn't that long, but just kind of follow along here. Here's the proof. Okay, so we're saying we got two positive numbers, x and y, and they're both less than or equal to 10. So what does that mean? We got two numbers, x and y, between 0 and 10, including the 10, not including the 0. Then we just go from there. We're assuming this is true. X is between 0 and 10, 10 inclusive. The claim is that we can then say that this statement right here is true. And that is, well, we have this value of y, which we're assuming to be positive. And so if I were to multiply this compound inequality through by a positive number, then it's not going to have to worry about switching the inequality signs or anything like that. And hence 0 times y is 0, x times y is some number x times y, and 10 times y is 10 times y, whatever that is. Moreover, because we know that this is also true, part of the assumption that y is between 0 and 10, including the 10, then we can also say that this statement right here is true. Now, where did that come from? We already know that y is positive, and then x at most can be 10, right? X less than or equal to 10. So if I just take the previous inequality we just came up with and then just fill in the values with 10, it must be true. So in other words, this shows that for any two numbers, the product, x times y, if both of these numbers are positive and less than or equal to 10, then that has to be less than or equal to 10y. But then 10 times y has to be less than or equal to 100. Hence, by transitive property, this must be true, that x times y less than or equal to 10y, but again, 10 times y is less than or equal to 100. Therefore, it shows that the product of x times y is less than or equal to 100. So we actually just proved the contrapositive statement. We assumed that two values x and y that are positive, less than or equal to 10, then their product must be less than or equal to 100. Remember, that was the contrapositive statement right there. So we proved it. It proves the statement we're after because we just proved this, which was if not Q, then not P. Hence, this statement over here, if P then Q, must also be true because contrapositives have the same truth values associated with them. So we proved it. And you think about, it's just an example of how to utilize the contrapositive. You go back to the very original statement all the way up here. This one. If you had a product of two positive numbers greater than 10, then at least one of those numbers is greater than 10. So we could have tried to prove that statement, and it would have also simultaneously proved its contrapositive. But perhaps if we approached that problem and went through the proof, it might not be as straightforward or easy as using the contrapositive. So that's what a tool of the contrapositive is if you're trying to prove some statement and you're not getting anywhere, specifically a logical implication, then try the contrapositive and maybe things go a little better, which will allow you to prove the original one. So that's it. That's your example. Hopefully you followed along with the reasoning. And that's it. Until the next one. The next one we're going to look at something called a contradiction, another way to prove some statements. So I'm out. Short beats coming. late.